Good morning, everyone. Welcome to today's presentation. I'm excited to introduce you to the banker's algorithm. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. In this session, we will explore how the banker's algorithm helps manage resource allocation and avoid deadlocks in operating systems. We'll cover the basic concepts, working mechanism, and some practical examples. So let's get started. Today, I want to introduce you to the banker's algorithm in operating systems. This is a deadlock avoidance algorithm that was proposed by Edsger Dijkstra, one of the pioneers in computer science. The main purpose of this algorithm is to help the system allocate resources in a way that prevents deadlocks from occurring in the first place. What makes the banker's algorithm particularly interesting is that it works by ensuring that, after each resource allocation, the system remains in a safe state. This means the system can still allocate resources to processes without risking a deadlock. In essence, the algorithm acts like a cautious banker, only approving resource requests if it can guarantee that the system will stay safe afterward. This approach helps maintain system stability and prevents the costly consequences of deadlocks, which can severely impact system performance and reliability. Throughout this presentation, you'll see how this concept fits into broader strategies for managing resources efficiently and safely within operating systems. Let's talk about why we need the banker's algorithm. First, deadlock happens when processes are holding resources and waiting for others, creating a cycle that prevents any of them from moving forward. This situation can really cripple system performance. Now, to handle this, there are two main approaches: prevention and detection. Prevention tends to be quite restrictive, often limiting resource allocation options so deadlocks don't occur at all. Detection, on the other hand, involves allowing deadlocks to happen, but then identifying and resolving them, which can sometimes mean rolling back processes, an approach that can be costly. That's where the banker's algorithm comes in. It dynamically checks whether the system is in a safe state before granting resource requests. This way, it ensures that resources are allocated only when it's safe to do so, helping us avoid deadlocks altogether. Overall, the algorithm provides a proactive way to manage resources efficiently and keep systems running smoothly. Let's now explore some key concepts related to system states. First, a safe state is when all processes in the system can complete their tasks without running into deadlock. This means the system is in a stable condition where resources are allocated in a way that no process is left waiting indefinitely. On the other hand, an unsafe state is a situation where there's a possibility of deadlock. It doesn't necessarily mean deadlock has occurred, but there's a risk that it could happen if resources are allocated carelessly. Because of this, the system must be cautious and only grant resources when it remains in a safe state. This approach helps prevent deadlocks and keeps the system running smoothly. Connecting this to our overall theme, understanding these states is crucial for designing effective resource management strategies that ensure system stability and reliability. Let's take a closer look at the data structures we use to manage resources in our system. First, we have the available vector, which tells us how many resources of each type are currently available. Think of it as a snapshot of our free resources at any given moment. Next, there's the max matrix, which shows the maximum demand of each process for every resource type. This helps us understand the worst-case scenario for resource needs. Then, we have the allocation matrix, which indicates how many resources are already allocated to each process. This is crucial for tracking current resource distribution. Finally, we calculate the need matrix by subtracting allocation from max. This gives us the remaining resources each process still requires to complete. Connecting all these points, these data structures form the backbone of resource management, enabling us to monitor, plan, and ensure safe resource allocation across processes. Let's walk through the steps of the safety algorithm. First, we start with work equal to the available resources, and we set finish for all processes to false, indicating we haven't completed any process yet. Next, we look for a process I such that finish I is false, meaning it hasn't finished yet, and its need is less than or equal to our current work. This means the process can proceed with the resources it needs without causing unsafe conditions. If we find such a process, we simulate it completing by adding its allocation to work, effectively releasing its resources back into the pool. We then mark finish I as true, showing this process has finished safely. We repeat this cycle, finding such processes, updating work, and marking processes as finished, until all processes are marked as finished. When that happens, we know the system is in a safe state because all processes can complete without deadlock. This iterative approach is at the core of ensuring the system's safety, helping us identify whether a given resource allocation is secure. Let's walk through the steps of the resource request algorithm. First, we check if the requested amount for each resource, request I, is less than or equal to the remaining need I, for that process. If it's not, we immediately flag an error because the request exceeds what the process still needs. Next, if the request is within the needed amount, we then see if the available resources, available, can satisfy this request right now. If they can, we proceed by pretending to allocate those resources, just to see if it would lead to a safe state. This brings us to the crucial step, using the safety algorithm to check if, after this hypothetical allocation, the system remains in a safe state. If it is safe, we can confidently grant the resources. However, if it's not safe, the process must wait, and we deny the request for now to avoid risking a deadlock or unsafe situation. These steps are vital because they help us manage resources efficiently while ensuring system safety, which ties directly into our overall goal of deadlock avoidance and system stability. Now, let's look at this example to understand how the safety algorithm works in practice. We have a set of processes, P0 through P4, and resources A, B, and C with their respective quantities. The matrices shown, allocation, max, and available, are essential for our analysis. Our goal here is to apply the algorithm step by step to determine if the system is in a safe state. Essentially, we're checking if there's a sequence of processes that can all complete without running out of resources. By examining the matrices, we identify whether the current resource allocation allows us to find such a sequence. If we can find it, the system is safe. If not, it's unsafe. This example highlights how these calculations are crucial for avoiding deadlocks and ensuring smooth process execution in resource management. It's a practical demonstration of how the theory we discussed earlier applies to real-world scenarios. Now, let's talk about some key advantages of this approach. First, it avoids deadlocks dynamically ***. That means the system can detect and prevent deadlocks as they happen, rather than relying solely on preset rules. This makes the system much more robust and adaptable in real time. Next, it provides safe resource allocation ***. Essentially, it ensures resources are assigned in a way that prevents unsafe states, protecting the system from potential failures or bottlenecks. And finally, it's efficient for systems with limited resource types ***. When resources are scarce or specific, this method makes optimal use of what's available, ensuring smooth operation without unnecessary delays. These advantages really highlight how this method enhances system reliability and efficiency, fitting perfectly into the overall goal of creating smarter, more resilient resource management strategies. So, one of the main limitations of this approach is that it requires knowing the maximum needs in advance. This means you have to predict the highest resource demand your system might have, which isn't always easy or even possible in dynamic environments. Another point to consider is the high computational overhead. Essentially, the calculations involved can be quite demanding, especially for larger systems or more complex scenarios. This can impact performance and make implementation more challenging. Lastly, this method isn't really suitable for systems where resources change frequently. If your system's resource requirements are constantly shifting, then this approach might not adapt quickly enough, leading to potential inefficiencies or issues down the line. So, while this technique has its strengths, these limitations are important to keep in mind when deciding if it's the right fit for your specific context. Let's wrap up with a quick summary of the key points we've covered today. The banker's algorithm is essential because it helps ensure deadlock-free operation by checking for safe states before granting resource requests. This proactive approach is what keeps systems stable and prevents processes from getting stuck waiting indefinitely. It's worth noting that this algorithm is mainly used in theoretical models or controlled environments where safety is critical. While it might not be practical for every real-world system due to its complexity, it provides a solid foundation for understanding how to manage resources effectively. In fact, the principles behind the banker's algorithm have influenced many modern resource allocation strategies. By understanding these core ideas, we can better design systems that are both efficient and reliable. So, in essence, this algorithm not only helps prevent deadlocks, but also serves as a stepping stone for developing more advanced resource management techniques in today's computing systems.